Let's also find some partial derivatives of this function and interpret those. This is different than implicit differentiation. I can, well, call the output z, for example, and I can find the partial derivative of this with respect to x. Remember, we use this fancy curvy d. You can still say dz dx. The fancy letter is used just to indicate this is a partial derivative, meaning this function involves more than one variable, more than one independent variable. There's nothing wrong with using an ordinary d. It's just not traditional. Treat the x as a variable. Here, treat the y as a constant, not a function of x. Which one's right? Is it a function of x or is it not? It depends on how you're thinking about it. How you think about things in math is, you might say, almost everything. It matters the way you conceptualize something. For the curve near points, it does pass the vertical line test. You can think of y as being a function of x. For graphing this in 3 dimensions to get a surface, x and y are thought of as varying independently of each other in an xy plane, and then z is determined by x and y. How you think about it matters. So now I treat x as the variable, and I treat y as a constant. So the derivative of this with respect to x, right there, is 10xy, and that's it. That's the derivative of 5x squared y with respect to x. There's no extra dy dx, because I'm not assuming y is a function of x when I do this. I'm assuming y varies independently of x. And when I think about partial derivatives with respect to x, I'm imagining y is constant. You can certainly do such imagination. You can certainly assume y is constant if you want. So I treat the y as if it's a number, a fixed constant. And constants like the 5 just get carried along when you take the derivative. So that's why it's still there. But it's not a function of x, so I don't multiply times dy dx. Here, I don't get 4y dy dx. I literally get 0, because y doesn't depend on x now. Here I get 0 as well. Here I get 0. There is the partial derivative with respect to x. It does turn out, for the purposes of understanding what's going on, to factor. Anything that can be factored out, like nx can be factored out. That's helpful sometimes. Oftentimes when you want to use partial derivatives, we're not really going to use it right now. We'll use it in chapter 4. Partial of z with respect to y, treat the x as a constant. So x cubed for this derivative differentiates to 0. For 5x squared times y, the 5x squared is acting like a constant. It just gets carried along. So pretend it's a 10. You know, the derivative of 10y with respect to y is just 10. The y goes away. I get 5x squared here. The derivative of this with respect to y is indeed 4y, and the derivative of that with respect to y is minus 4. Minus 11 is still a constant, so I get still a plus 0 here. This simplifies to 5x squared plus 4y minus 4. These can be interpreted as rates of change. And I can use them to do linear approximations, just like in the one variable case. For example, I know f of 1, 2. I know f of 1 comma 2 is 0, right? I use that. I verified that in Mathematica before. I might want to estimate, estimate f of f of 1.2 comma 2.3. Now I'm estimating a multivariable function value. Should be close to 0, but not necessarily exactly 0. I've changed the inputs a little bit. The outputs will change a little bit from 0 to something non-zero. I can use these derivatives to figure out how much. How? Well, again, these derivatives are rates of change. I can plug in the point in question, 1, 2, that I'm letting x and y change from into these derivatives. I can find the partial of z with respect to x evaluated at the point 1, 2. Plug that into this formula. Get 3 times 1 squared plus 10 times 1 times 2. That's 3 plus 20 is 23. We've seen that before. Find the partial of z with respect to y evaluated at the point 1, 2. Plug it into here. 5 times 1 squared plus 4 times 2 minus 4. 5 plus 8 is 13 minus 4, 9. We've seen that number before. We knew the slope of the level curve at the point was negative 23/9. Not unrelated to the 23 and the 9 that we're getting here. To do this estimate now, f of 1.2, 2.3, it's a very similar idea as the one variable case. Take f of 1, 2 and add the approximate changes that come from these linear approximations. The 23 is the rate of change in the x direction. Multiply that by how much x changes. X changes from 1 to 1.2. It changes by 0.2. That's delta x. The rate of change in the y direction is 9. Multiply that by how much the y coordinate changes. 2.3 minus 2. That's 0.3. That's delta y. F of 1, 2 is 0. What is this going to come out to? 23 times 0.2 is 4.6. 9 times 0.3 is 2.7. When you add those, you get what? Some 7.3. That would be your linear approximation. Is it right? I'm sure it's not exactly right. Is it close? It's hard to say. These derivative values of 23 and 9 are fairly large. That's the reason why the function value changed so much. How close is it likely to be? It's hard to say without doing it. F of 1.2 comma 2.3, it's 8.7 actually. We got 7.3. So not as close as you might hope. But if I use numbers that were closer to 1 and closer to 2, it would be a more accurate approximation. Let's try that even. Like if I was trying to approximate f of 1.02 comma 2.03. Now I've made delta x 0.02 and delta y 0.03. The linear approximation would be 0.46 plus 0.27, 0.73. What's the actual value? 0.74, not too far off. The approximations get better if x and y don't change very much.